Hello everyone, good evening. Do you know that we spend more than around 50 to 80% of time in pre-processing the data in a typical machine learning, or is it starting now? Or
Yeah, you can start. You can start. No issue.
okay, sorry, I'll start again then. Okay. Hello everyone, good evening. Do you know that we spend around 50 to 80% of time in any typical enterprise level ML project? Hello everyone, I'm Indranil Bhattacharya. I work as a data scientist at Renault Nissan, and I also serve as the teaching assistant for the software engineering course and mentor for the DL project course. And the topic for today's session is pre-processing is all you need. And through this session, through this workshop, I will try to convince you that with proper pre-processing, you can even tackle different data modalities and still use very simple model to develop predictive models. Um, so let us start. A brief agenda. So we'll start with why pre-processing is required. Then one by one, we will go through each data modalities, namely tabular data pre-processing, image, audio data pre-processing, and pre-processing of fixed data. So you can see that through this one. So as we keep on moving through this data modalities, we'll be giving you models newer abilities. Like an image will be giving a model ability to see, right? So let's start. Before moving into any detailed discussion about the modality itself, we have to first ask ourselves why pre-processing is even required. And often, so you all have already seen this, I hope, in the MLP course, but why not? Let's discuss more about it. There is a very popular saying that garbage in, garbage out. It's written here. But for this completeness sake, let's discuss about the points that for which we need this. We need pre-processing to actually enhance our model's performance. Almost always the quality of the data will actually improve your model's performance. And this also through pre-processing. Why so? Because through pre-processing, we help our model to learn more about the uh, we whatever we know about the domain knowledge, we try to inject those in our data itself. And we kind of do this through something known as feature engineering or pre-processing. And this actually also helps us to sometimes unlock insight. Why? How is that? When you have a very high dimensional feature space, like you have 100 features or so, and you have developed a model, but you don't know how your model is giving you the prediction, right? In that case, having a high dimensional space doesn't really help. It actually hurts you. So you can use feature dimensionality reduction technique or feature reduction technique to actually reduce the feature space. Or sometimes if you feel that the feature space is not enough, you need more feature, you can create those using feature engineering. So the key takeaway I have for this slide is that um, we typically try to stick to find whenever we get any problem statement or any data set, we try to find the best model for it, or we try to find out the best algorithm to hyperparameter tuning. That is the model centric approach. But but what we should do is we should start with well prepared data, or we should start improving the quality of the data itself. This is known as data centric approach, and we should start embracing this data centric approach more and more, even with newer modalities or more with different types of modalities as well. So let us start with tabular data pre-processing. It will be a quick recap because we have already seen this in the MLP theory or project course. But let's why not? We can discuss it. Whenever we get any tabular kind of data, we have already seen that the data is always messy, comes as a messy artifact. So we what we do is we if we think that we have any unwanted characters or any unwanted values, we remove those. If we think that we have outliers and those are going to affect our model's performance, we remove those or sometimes even keep those. And for a classification type of project, you have already seen for imbalance data set. When you have class imbalance, we also do a lot of augmentation. So that is like a cleaning process. Then what we do is very classic transformation, normalization, and standardization through min, max, scalar, max, absolute, standard scalar, all those. We also do encoding, feature extraction to TF-IDF. All these are actually you have already seen. And what I was saying in the what I was referring to in the previous slide is we also create more features that is known as feature engineering. And we also sometimes reduce the feature, something with something known as PCA or something non-linear like PSNE, right? So if you forgot about something, so if you are not able to remember these things, please go and revisit the machine learning theory course. But let us now start with the new modality that is image data processing. This might be new to some of you. So here with this, you are going to give your model the ability to see something because your model really doesn't see. Your model only can process raw numbers. It doesn't see anything. So with proper pre-processing, you are going to give your model the ability to see. It's very interesting, at least for me. So maybe I hope it will also be interesting for you. So first of all, you may ask that image is a very nice little artifact, right? We see image, we share image all the time, but why pre-processing is even required? Because anyway, we can always understand it very easily. But we have to understand image from a different perspective when we have to develop models for the computer vision task. Image is nothing but a captured or a sampled version of the real world scenario or the real world phenomena. What do you mean by that? Let's say there is let's say some real some fireworks are going on, some fireworks show is going on, and you are capturing it through your smartphone camera. Here you are actually sampling from the real world. That is, the firework is being that activity is being shown and all those things, and you are capturing it through something known as camera. That is your device. Now the quality of the image will depend heavily on a lot of factors. First is your capturing device itself. It has a lot of configurations like what is the highest resolution it can get, right? And a lot of other, if you are a photographer, you already know what kind of configurations I'm talking about. And that is not only about it because camera configuration we mostly will be able to um, control. But the problem is about the real world phenomena. Remember that here there is something happening in the real world where you don't have any control, right? So here here a lot of other things plays a very crucial role, like the time of the day. In a very typical sunny day outside, the quality of the image, the quality of the image will be very clear, right? But when you take the same image during the evening or during the afternoon, the image quality will be very bad because the daylight is not that much available at that time. Similarly, a lot of other things can play a very crucial role, like the amount of pollution in the air, the amount of dust in the air. A lot of other things is also there, and these are actually something that you don't have any control over. So you capture the image, and that becomes our training data. We use this image data for developing models. And once you start developing your model, will start encountering these issues. One is inconsistent size. Let's say you are trying to classify an event on a few categories, and you have sent five different persons to capture or to take images through their handheld cameras or something, and they all came back with some of the images, and you suddenly will see that the image size will probably be different. What do you mean by that? Maybe someone has captured 200 by 200 pixel image. Maybe someone has captured a very high quality image. Uh, so you can immediately understand that in a very high quality image you have a lot of details. But when you have a very small, smaller size image, when the resolution itself is very low, you are not able to capture all the details that you wanted to capture. And a lot of other things like you have a whole bunch of different what do we say this types of image files possible, like jpg, png, jpeg, svg, all this, and all this comes with its own features and also its own pain points. As I said, varying light and color, you can very easily see that when the color is very dull, or when the lightning is also not there, it's not very abundant, you will have completely two different image of the same object itself. And we as human can sometimes understand what is there, and we can understand what is happening, but for machines it's really difficult, sometimes even impossible. There is also something known as noise. It can also come from the real world phenomena, it can come from real world phenomena, or it can also come from a very simple smudge in the lens, right? And last but not the least, which is the most difficult problem, that is limited data. When you start developing models for the computer vision task, you will soon realize that we will always have a very less number of images to work with. And when you have very high stake problems radiology related data and all those things becomes even more difficult to get high quality and properly annotated images, right? So augmentation. So these are only a few set of problems that we face, and for all this we need different sets of pre-processing routines, right? So just to give you two examples, let's say you are developing an image classification model, and the training data you got was had very high quality images from, let's say, DSLR camera. And at the test time, whatever image you got were actually very poor quality images, maybe taken from very old handheld cameras or mobile cameras. So what you had is the original training data had clean images, but at the test time you are getting noisy data. Right? So how will you deal with this problem? Here the problem is not that straightforward, because you cannot really use always this. You cannot expect the same amount of performance with this noisy data, because your model has not seen this much noise during the training. So it does not even expect any kind of outliers noise in our trail data, in your incoming data. Right? So what you have to do is that if you really want to go with this setting, what you can do is you can actually either denoise the test data or the incoming data you have through something very standard and straightforward like Gaussian blur. We all know that if we apply Gaussian blur, the image can get the noise can be denoised, and we can use those filtered images as test time to improve our model's performance, to actually improve our inference performance. It can also be the opposite way around, right? When you started developing a model, maybe the uh, so now it is not so with Gaussian blur, you can you cannot remove all the noise that are possible, and there are a lot of other things that can go wrong with it. So sometimes what we can do is we can augment the image. What do you mean by augment? So we can actually, let's say you have. So let me talk about augmentation, and then I'll show you how we can use noise augmentation. So let's suppose you have 100 images, only 100 images to start a classification job. So it's not enough. So what you do is, for every image in your training data, you rotate it by 6. some degree and you create one more image. You flip the image by some degree, you flip the image and you create one more image. You crop a certain portion of the image, you create one more image. You add some color jitters and you add one more image. So what you have essentially done is, and a lot of other a mix of different augmentation can be applied, and you can create newer image from the training data itself. So you can very quickly do the math. Let's say from each image you are applying 10 different augmentation. Then from each image you are getting 10 more images, right? So if you started with 100 images, you would you will be having after you do this, you will be ended up with 100 times 10, right? So 10,000 10,000 samples to work with. And the best part about image data is you are not essentially changing anything about the image itself. You are only you're kind of modifying the image in such a way that the ground truth or the relationship between the physical phenomena and the target level is not changing at all. So you have just rotated the image by some degree, but the whatever object was there in your image still stays there, right? And the goal here is that if your model is robust enough, it can still detect it. So you have not change anything. You can still use the same ground truth level, and now you have 10 times more images to work with. That is why augmentation is a very powerful technique, and we almost always use augmentation for image data preprocessing. Now let's go back to the noisy data. So your original data was very clear. There was no noise, and at the test time, whatever data you had were very noisy. So what you can do, whatever original data you have, non-noisy data, you can add some more noise, right? And then you can start training your model. Now immediately you can see that your model will start seeing some noise during the training, and your model will now learn about the noise. And at the test time, if you now start feeding noisy data, it will still be able to perform well. That is the objective of augmentation. So typical workflow is you load the data and then you define the transformation. So these are the transformation that you have to define how you want to perform it. You can either perform it on the training data directly itself and then feed it to your model, or if you are using packages like PyTorch or TensorFlow, you can define it in the model itself. Okay, yeah. And please note that whatever augmentation we do only on the training data, not on the test data, right? So please remember this. Even if you define it in your PyTorch model or your TensorFlow model, those augmentation are not applied on the test data. So I'm not whatever thing I'm saying here in this workflow and all. The proper notebook with proper comment and documentation will be shared after the session. So don't worry about the code itself. And then you train the model. So that is the typical workflow of image data processing. Now let us start with audio data preprocessing. Okay, and here you are going to give your model the ability to hear, and it's I when I first learned about it, it was very fascinating to me that now my model will be able to listen properly. Like now, what is audio data? First, we have to ask ourselves. We all have heard. We have always, even now, you're hearing as I'm speaking, right? Audio signal that are coming to that are going through your headphones and all. Now, if you want, whenever you have to use work with audio data, you should have some signal processing background or some signal processing understanding. So, if you are really interested to work in this field, please go. I'll share some resources. Go and have some more, do some of your more self study on it. But I'm just going to cover some basics of it. So typically, you have seen that we represent the audio as waveform, and this is like a array where we show the amplitude over the time, right? Like a sine curve or something. There is something known as sampling rate. So sampling rate is something. So I'm speaking something, right? And Google Meet is capturing my audio, but It is going to it is defined like per second how many audio samples are captured by your capturing device. Okay? So you can I hope you can understand that the higher the sample rate, the better the quality is. Because per second you are capturing more information about the signal itself. So sampling rate is a very typical, very critical quantity when you have to start working with any audio data. And bit data and all those things are there. I will share some resources and you can go through those to understand more about the audio data itself. So that was about and you will have to have some basic math background to understand a lot of other stuff. That was the nitty gritty of the audio data itself or the signal itself. But given an audio, given we all are data scientists, right? We love to develop machine learning models to predict something. Given an audio data as a data set, and you are asked to develop a predictive model, how will you approach that problem? I am going to give you a recipe of that, and if time permits, I'll also show you a demo of it so that you can also get started with it, right? So we can actually do some. So audio is like a encoded data. Your model doesn't understand anything about it. Just to be very clear, your model or your computer only sees numbers, zeros or ones, but your audio is like a enco- an encoded format, right? And you have to kind of somehow give your model ability to listen like us. How will you do that? We have to extract features from the audio data, right? And we can do this extraction through a lot of different techniques. But here I have given two very simple process. These are not really simple, but these are well understood and easy to use processes. You can use this to actually um, extract features. One is spectrogram. What do you mean by spectrogram? We capture audio as waveform, but so if you are familiar with Fourier transformation, it will be very clear to you. But if you don't know, in a typical audio signal, we have different frequencies. Like it's just like if you have an f of x, which is a non-linear combination of different xi's, and your task is to understand what all xi's were there in your f of x, were used to develop your f of x. So given an f of x, which is your audio signal, what all are the frequencies there in your signal? This is the mapping you have to actually uh, you have to build through spectrogram. We do this through something known as Fourier transformation or short time Fourier transformation. Even I don't know very detailed things about it because it's the math is really deep. But uh, I will share some resources. You can go through it and understand more about it. But what we really do is we kind of go through the signal and extract what all frequencies are there uh, in your uh, in your signal. Now, if you have two different signals, and those two signals or the two audios are very close, similar to each other, then they will have very similar frequencies, or their spectrogram will be very similar to each other. So we can use this concept to fingerprint or you can say matched fingerprints of audio signals, right? That is why spectrogram is a very popular, well-known technique, and we can also use it for visualization. We can also use something known as male frequency statistical frequency. It is known as MFCC. So it's mouthful, but it is a very powerful technique that we can use to extract information from the audio data itself. And I hope you will be very happy to hear this. You, if we have time, I'll also show you how to do that in your notebook. So, what is MFCC? Or why MFCC first? MFCC actually uh, extracts the feature from your audio data. That is one thing. But why do we need MFCC? Why is it even preferred, or why do you have to start with it? The reason is uh, the representation, whatever it builds, sounds very similar. Like it actually mimics the human auditory system's response. Meaning, uh, just like you are hearing, your model will hear the sound just like you are actually experiencing it in your through your own ears. I'll repeat once again. So you have an audio signal and you are listening to it, and you have also given this data to MFCC, and then that data is being sent to your model. The claim here is that the way the model is going to experience the audio will be very similar to how you are going to experience the audio. Here, you meaning the human, right? It's a human level performance we are speaking about. It is going to. This is a very strong feature about the MFCC. It actually mimics the human auditory system's response. How we really do it? Once I go to the notebook, I'll show you. And this can be now used because this has a very powerful property now, because it can actually mimic our ability to listen. Right? So we can use this to have something known as speech recognition or any speech related property or any music recognition related property. We can actually, for this task, we can actually start using it. Before going, I think I had some time, I can go to the demo. So before going to the demo, we have to understand what all things we have to see, what all things we have to keep in mind when we start any audio data preprocessing project. First is sampling data, as I said. When the sampling rate is high, that means you are capturing more information per second. When the sampling rate is low for a signal, you are capturing lesser amount of information, right? Now you can imagine that if you have this different sampling rates for different audio signals, and you are given let's say 100 different audio files to classify, you can imagine that one file will have more information, one file will have less amount of information. So it will become very difficult to even for us to understand what kind of information it captures. Right? So whenever we start any project, we try to make sure that all the audio files have the uh, um, if not same sampling rate. Then there is this thing called mono versus stereo. In the typical real world scenario, we prefer stereo sound over mono channel sound. But when you develop ML models, we really sometimes don't need this extra information. So we can convert it to mono this time. Handling variable length. You can have audio one, let's suppose you have 100 files. One audio is 2 seconds long. The other audio file is 2 minutes long. What will be happening in that case? So now let's take a step back and uh, compare it with a classical text data preprocessing. Uh, in one example, you have 100 words in your sentence, and in the other example, you have 1,000 words. 1,000 words will have. So if you don't do anything about it and you start using this, the higher the longer sentence will have more words to um, show, right? And the embedding space will be 1,000, and for the shorter sentence we have only 100. So this there will be a mismatch, right? The input data mismatch, dimensional mismatch. So what we essentially do is we either we truncate the longest one and like match the length with the shorter one, or we pad the shorter one to match with the longer one. Okay. So these are a few things that we typically do to process we take care during the pre-processing. Now I will share. I'll go to the demo part of it. Let me know once you are able to see this page, Bhattacharya page. a white screen. Are you able to see a white screen here with a bunch of code? Anyone? Can anyone confirm, please?
Yeah, it is very.
Yes, yes.
Okay. Okay. So what here we are going to do is we have this. We have taken this data set. Here the objective is to we are given a set of a bunch of data, and the competition is like we have to detect deep fake or generated data, audio data, and that too in Indian languages like Assamese and all the other languages. I don't know if you will be able to. I'm not sure whether you are able to hear it, but these are actually playable, and you can see it for yourself. And
Yeah, I hear the audio.
okay, okay. So here you have this audio, and the text is given, and your task is to predict whether it is a deep fake audio or not. Right? And what we have done here is we will show you how to create this pipeline. So here we have loaded the data, and it has all these different attributes. I'll just take time. Alright. So now what we are going to do is we are going to use MFCC as a feature extraction technique to extract features from the data. So what is MFCC once again? It actually extracts feature from the audio data itself, and this is done through MEL scale. What do you mean by MEL scale, or how it mimics the human hearing? We were saying this thing multiple times. So the key observation is we human we are very sensitive to lower frequency ranges. We as human are actually we are very sensitive to lower frequency changes. So when there are two signals and the signals have lower frequencies, then we'll be able to detect the differences between the two very easily compared to the two when those are in higher frequencies. So that's the observation with which it kind of wraps the audio and creates a scale. And this scale is being used here to kind of create the representation. I'll not. So here the process is also I have listed here. I'm not going to talk about it. It's like a mathematical process, but we are going to use this MFCC extraction to now to have this demo. Right? So here I have created a pre-processing function, and so what it essentially does is it loads the data using something known as librosa. So here I am just loading the audio data. You can see, and sampling rate I have given none, but I think it was supposed to be 33,000 or something. It is given here, and we have loaded the data. We converted it to NumPy array, and then we are using librosa to extract the feature space, MFCC features, right? And for each of the time step, it is going to extract the features, and it is going to give us back the feature representation, and I'll show you what is the output. So it will have this different, what do you say? Different. These are you can say principal components or kind of that kind of understanding you can have. So here, these are the feature representation, and these are the feature name that we can say. Okay. And we have extracted around 19 MFCC values, and these are now my features. Then what I have done is I have converted this to NumPy array. These are just some code manipulation to make this thing work, but there is nothing fancy over here. And now what I have done is, sorry, what I have done here is I have used the same train test feed API, this should ring a bell from the scikit-learn pipeline, and I have just created the training validation dataset, and then use this simple logistic regression to classify it. And now you can take a look at the data, the performance. This is for training, this is for test, and here you can see the performance. The average F1 score, the macro F1 score is 0.72. And just now see the average, the macro F1 score on the test sheet is 0.73. Now let us take a step back. What have we done here? The data was in this format. We So if you have just completed MLP, you must you have you're probably thinking that I don't know how to process this audio data, but I really want to work in this field. This is like a very interesting competition. So what I have done is we have taken this unknown format, unknown to us format, and then we have done some very specific pre-processing known as MFCC, and then you have reused the same pipeline whatever you have learned in your MLP course, and even with a simple linear model like logistic regression, we are able to achieve 0.73 F1 score. And just to and that's not enough. That's not the end of the story. Where you can see I have taken only 10,000 samples. The original sample, I think it was 31,000. I have not used even my full training data to train it because my kernel was crashing. Uh, Confession, just a confession, but here I have used 10,000 samples only, right? But I can increase my my computer. I could have trained it, right? So this is not even the full power of this system. So my goal was to show you that even with very simple simple algorithms like logistic regression, you can actually tackle very complicated and very serious problems like this, deep fake detection. And I don't know if you know it or not. This was actually one of the competition of the deep learning practice course in the degree level. So it was like a good thing to have. Right? It was not easy to tackle. So that's about it. So I'll now go back to my slides. I don't know why. Okay, I'll share my screen once again. Just give me a minute. So that's not the end of the story. So I'll now go to, there is one more modality left, that is pre-processing for natural language. What do you mean by natural language? That is basic text. Right? That is text. Okay. So here you are giving your model the ability to read, just to make it more clear. So when we encounter audio, when we encounter text data, we have to do a lot of pre-processing. And for us, it is very easy when we know the language. If you're having, let's say, Russian language, it will not be easy anymore. But when you have having English or your mother tongue, it will be very easy. So it's the cleaning text is also very subjective task. And what we essentially do is we lowercase the data. Whenever we see any kind of punctuation, we remove that because this punctuation doesn't add up any. You can argue that, but really doesn't help much in our model development. And whenever we see any typos, like if someone has nowadays in the SMS language, in the SMS lingo, we never almost never type the actual word. So when you start collecting data from those kind of sources, you can quickly imagine that why this spelling correction is required. So that is one more reason to add this here. And once you have done this basic set of cleaning, like this set of cleaning is very specific to the data you have or the corpus you have. But then comes the actual routine task, that is tokenization or normalization. Once again, your model does not know anything about the language. It can only see numbers. So how will you send this slide to your model? What you do is we tokenize the data So this coherent set of text we convert it to something known as these are token, right? These are individual words, unique words that are available. Then sometimes we remove the sorry we remove the stop words like the a and because it even though these are for grammatical purpose, it doesn't add any information to the text. Then what we do is these are like some very basics of NLP. So we do something on as stemming and lemmatization. Stemming is like in language comes in all sorts of forms, and because just because we have grammar, we have different forms of the same word, right? So what we essentially do is we reduce the word to the root form. Let's say this is an example. Studying is you have some word like studying, right? And then you also have another word like studies. These two are essentially the same word. Just because we have some weird grammatical rules, we have added some extra words at the end of it, right? But these are essentially the same word. So if you now want to tokenize it, and you have two different tokens, that's a typical waste of resources, right? So what we try to do is we kind of take it back to the root word. That is, here we are saying study or something, right? We can also say study, study, right? That is the stemming part, or we are making it crude. You can also have something known as lemmatization, where we can actually, from studying, we can actually, from these two different words, we can actually return back the original context for that is studying. And these are like very well known NLP techniques. Now you have done some real pre-processing, and then what we essentially do is here we represent the word. How we represent the word? we we all have seen bag of words in the typical MLP setting where we count the occurrences of each individual token. What are taken once again? These are the tokens, right? So how many times foxes appear in my sentence in my first row? We count it. We put it as a number. That becomes my feature matrix. One step further, uh, PFI there. What we do is, if we encounter more rare words, we give more importance to it. If we encounter words like the and uh, I'm eating, these are like very frequent words, right? So these are most likely will not going to give you something very crucial information. So we don't give much importance to the uh, more abundant words. And then we just once again, this is like a weightage, and we calculate the count of it. We multiply those. That is your TF idea. And then you have word embedding. That is something known as word to way glove. So here we also try to capture the semantic relationship. This is the first time we are hearing maybe this term in this slide. So what we try to do is it not only captures the rough counts of the word, it also captures the context of the word, or it tries to look at some neighborhood words of the given context of your sentence. I'll take the question at the end. That will be good. So now the real question is, uh, which one would you use? I have given three examples, not three, I think five. But which one will you use in your next NLP project? The real answer should be no, none of that, none of those. You will be using something known as transfer learning approach. What do you mean by transfer learning approach? Here we use pre-trained model. Someone else has already like trained your model, and now you are going to use those pre-trained model that has already learned a lot about your language itself, defined languages as well. And now you can use those pre-trained model to extract information about the language. Right? So we can use transformer-based models like BART, Robota, or this kind of thing. These are very These are like the de facto standards nowadays. So I don't have to really tell you about the names of it. But what we essentially do is whenever we have any kind of task in hand, we try to know as much as possible about the task in hand, like what kind of language we can encounter, what kind of text we have, what is the domain of this, and then based on it, we go and try to find a suitable model for this kind of task to extract features, or sometimes even for this task. Right? A model was trained on multilingual data. I'll just give an example. Llama 3 models were actually trained on multilingual data, even with a huge corpus of actual scientific books. So now, if you have to work on a very scientific problem, when you have to classify scientific text, you would probably choose some version of llama, or maybe you'll fine tune it, right? So that's how you will match the use case first. Then you'll take the model off the shelf from, let's say, Hugging Face or something. You tokenize the data, you create the tokens, you embed the data, and if you want to improve your model, you can also fine tune it, right? So that's, and I think I have some time, so I think I can show some demo as well. So what in this notebook, what we have done is we have taken a data set from a pro. Just give me a minute. Okay, this is the competition. Yes. So here you have to actually predict whether a text is a tweet is about disaster or not. But the data, I will also show the data. The data has some natural language, and you have to predict whether it is a disaster tweet or not. Right? You have also have some other features. Let's come back to the data set quickly. So we have actually talked about three different types of embedding. One is TF-IDF. Then we also talked about glove embedding, and then we have also talked about transformer-based embedding. Right. So we have given you some code for you can use this to actually embed the text. So we have actually loaded the data set, and what we are going to do is we are going to embed the text using three different embeddings. And what we are going to do is we have to choose which one is the best approach to encode our text, right? That is something we will play a very crucial role. So we have a few approaches: traditional embedding, dense embedding, transformer based embedding, and this one I'll skip. So these three I have as option, right? So how will you select the best one for your use case? I'm just giving a very rough example, like quick data example. Uh, I have selected a proxy of for evaluating the quality, something known as a sentence similarity. Okay, given two sentences, if the two sentences given two very similar sentences, if I am getting the similarity very high, then I'll say that the model is good. When the two sentences are not similar to each other at all, and still if I'm getting very high similarity, then I can say that the model is not good. So similar sentence, high similarity, dissimilar sentence, low similarity, and we are going to use something known as cosine similarity to measure it. I have given detailed explanation about it, and now we are setting up the experiment. These are the two similar sentences, and these are the two dissimilar sentences. Okay? I'm just skimming through it. You can go through the notebook at your own pace, and you can see that we have used TF-IDF embedding here, and for TF-IDF, for both of these pairs, the similarity is zero. Why zero? I think all of you are more than qualified to answer this question. Maybe someone can ask at the end as well. Uh, Now you can use glove embedding, or you can the one that I said, this one, a lot of text with dense embedding, or the representation which tries to capture context. We have used here the glove embedding, and here you can see when we are using similar pair meaning these two sentences, cosine similarity is very high. And when you have dissimilar sentences, the cosine similarity is below zero point 0.5, which is acceptable. So now we have started capturing some context. The theory I told you before, we are able to see it in action, right? When cosine similarity is high, that means two vectors, or the two embeddings are very similar to each other. So that means we are able to capture more meaning, right? So that this means we are able to capture better representation, more meaning, more context from the data compared to what you have done in your MLP course. Zero. That is not the correct option, right? Correct answer. Now we are going to use something known as transformer based model or the transfer learning approach. Now see the dramatic difference. When the sentences are similar, the similarity is 0.7266, which is very high, or which is high. But when the sentences are dissimilar, I'll once again show you the example. The cat sat on the mat. Quantum computing could revolutionize science. These were completely different sentences, right? And you can see transformer is actually saying that these two sentences are very dissimilar. It is not even zero point 0.1. Right? So that's how you can actually say with just go by going through this short exercise that given these three examples, transformer based model with transfer learning approach is a better technique to encode your data. Now, what will you do given this data? You will, so you have the text, you have the target, it's a supervised learning task. You will use a good transformer based model that captures context very well for your use case. You will embed it using that. You will get a feature matrix. You have the target. Then you can start using a simple logistic regression, your simple scikit-learn model, or even PyTorch model for that purpose. And then actually you can use this to make submissions. And actually, we have a lot of other explorations as well in this notebook. You can just go through this. And before closing this, I will once again try to give you one more nudge. This is one more Kaggle competition. I hope you guys are not bored. So I'll take my chances. So here the objective is to predict the biological function of the protein. So what is the objective here? We given a protein sequence. What we have to do is we have to actually predict what kind of biological function the protein will exert. And if we go through this competition, they have very clearly said, uh, I'm not able to find it, but you can go through this competition, and they have very clearly said that this competition is actually evolving. Even the scientists don't have proper answer or the proper ground truth for the test data. They are doing it as if we will be working on this project. And once the scientist actually creates the ground truth at the actual level, your prediction will be computed. Your final score will be calculated. And what is the so you can imagine how difficult it is to for even the scientists to work on this field, right? They are actually the stalwarts in this field. I'll show you the data as well. This may seem daunting, but I'll show you. It's not that much difficult. You have given some protein sequences. You can say these are IDs, and you are given also the what do you say? The actual target, that is the biological function. It doesn't look like biological function, but it is what it is. For this particular protein, the biological function is this. Okay? This is your training data, and you are also given the sequences data as parts of it, first of it. Yeah. So I'll show you why I am talking about this. This may not be making any sense to you now. So this is the actual protein sequence. It is a very long set of string. Given this string, so you will be asked that I'm giving you this string. Tell me what is the biological function of this protein sequence. So how will you approach it? You have already learned how to represent text data effectively through transfer learning, through transformers. This is nothing other than that. You just have to think carefully from the physical perspective, or you have to think from a biologist perspective. It is not only some gibberish text. Each of this amino acids will have to come in proper sequence to have some biological properties, right? So you'll have to also um, you'll have to actually preserve that sequential order, and you have to encode it somehow. Once you're done with that, you once again have the target ground truth level. You can just build a machine learning model and then make a solution. So at the end of the day, whenever you encounter any problem statement like this, try to look at the data, try to look at the the problem statement, and try to understand. Given this data, I know now to how to handle new modalities. So how would I approach this problem? If you start asking more questions, meaningful questions like this, I I can guarantee you that you will be able to make predictions in, let's say, a few months or so. Okay. With that, I will stop here. If you have any questions, please feel free to ask.